Okay guys, here's another video. We're still going to be in the same section, still reviewing the same things we did last time, which are simplifying trigonometric expressions and then also verifying or proving trig identities. So I'm going to go through a few from the Aries assignment that I had done. I posted on Aries, an extra credit assignment. Now, by the way, for those of you who are looking at the assignment on Aries and saying, well, wait a minute, it has a due date of such and such date. There are no real due dates for this. This is extra credit. This is all optional. Whenever it is you get around to doing it, then send it to me then. Okay, it's not due the next day. Aries by default just picks a due date of the next day unless you change it. And honestly, I just never feel like going in there and manually changing due dates because it's just another thing to add to the list of things I have to do when I create an assignment in Aries. So anyhow, if you see that, don't worry about the due date. Just, obviously it's due by the end of, I'd say May, but, that is what it is. Okay, so what I want to do is I want to go through some of the problems that I assigned on there. I'm not going to do the whole thing, obviously, because I've only gotten that assignment from a few people. If you're watching this and you've already watched the first video and you haven't done the assignment yet and you do some of these problems and you just copy them into your homework, it's not the end of the world, but I would like you to try to do it on your own before you refer back to what I'm about to show you. Okay, so what I did is I picked out some of the problems that I thought might be a little bit difficult, ones you guys may have struggled with or maybe currently struggling with to do. So I'm going to start with number 13. So number 13, it has 1 plus cosine of y over 1 plus secant of y. And I picked this one because I thought, what? People may not know where to go from here. So anyways, I typically look at stuff like this and first I scan for, do I see any kind of identities jumping out at me or something else that again, the more experience you have with these, the more you start to identify what things you may try. But anyways, on this one, nothing really jumps out at me. I'm not seeing anything that, is screaming identity that we have in our notes. And so then a lot of times our fallback, like I mentioned in the last video, is just, well, let's turn things into sine and cosine. Okay, whatever is not in terms of sine and cosine, let's see if that takes me anywhere. So that's what I would try here. So 1 plus cosine of y, that's already in terms of cosine. But in the denominator, I have 1 plus, well, secant of y, that's 1 over cosine of y. So, well, what did that do for me? Well, by turning secant of y into 1 over cosine of y, well, now I have this fraction down here. And so a lot of times when I see a fraction like that in these types of problems, I think, well, okay, between this fraction and this term, maybe I'll make common denominators. Maybe that will take me somewhere. So let's try that. So on top I get 1 plus cosine of y. In the denominator, if I make common denominators between these, well, this is just 1. So that's the same thing as 1 over 1. So this 1 is the same thing as 1 over 1. So I have a denominator of 1, I have a denominator of cosine. So obviously the denominator, or the common denominator, is cosine. So I'm going to multiply the top and the bottom here by cosine y over cosine y. So the result is I get cosine of y over cosine of y, that's equal to 1, plus 1 over cosine of y. And then, well, since I made common denominators, now I can add those two fractions together. So on top I still have 1 over cosine of y. In the denominator, if I combine these as one fraction, on top I get cosine of y plus 1 over cosine of y. So I have 1 plus cosine of y over this fraction, but again, if I'm dividing by a fraction, that's the same thing as me multiplying by the reciprocal. So this is the same thing as 1 plus cosine of y times the reciprocal of this fraction, which would be cosine of y over cosine of y plus 1. Well, what does that do for me? Well, 1 plus cosine y and cosine y plus 1, those are the same. And so what does that leave me with? It just leaves me with cosine of y. So this expression here simplifies to cosine of y. Again, I didn't really do anything fancy. I didn't see any identities. I looked at this and said, well, maybe I'll turn that into cosine. So I did. But once I did that, then like I said, certain things just start falling into place. You kind of get the ball rolling. And, you know, once I had this, I thought, well, maybe I'll make common denominators. And then once I combine them in one fraction, then, oh, well, maybe I'll multiply by the reciprocal. So once you kind of get started, suddenly, like I've mentioned before, the steps start to become apparent. So anyways, that's how number 13 should be done. So let's try another one. By the way, you are imagining things. I am not wearing the same shirt as the last video. The other one had long sleeves. This one, it just goes to here. So don't judge me through your screen. I do shower sometimes. Anyhow, let's look at number 15. So in number 15, I have secant squared x minus 1 over secant squared. And so again, I'm looking at that and I think, well, are there any identities that jump out at me? Well, I do have an identity, a Pythagorean identity that involves secant squared and 1. I'm not sure if maybe it turns exactly into that. So I'll think about that when I'll recall, oh, I have this Pythagorean identity that says 1 plus let me rewrite this. 1 plus tangent squared x is equal to secant squared x. Okay, so I have that identity. Well, here I have secant squared x minus 1. Well, I have the 1 sitting here. If I subtract that to the other side, what I do get is I get tangent squared x equals secant squared x minus 1. So I see this and say, okay, well, I have secant squared x minus 1. Well, what can I replace that with? Well, tangent squared x. So maybe that'll take me somewhere. So from this expression, now I'm going to rewrite this as tangent squared x over secant squared x. So, okay, well, here's where I'm at. Nothing else is really jumping out at me. However, again, a lot of times our fallback is, well, okay, let's turn things into sine and cosine then. So I'm here, I'm a little bit of an impasse, and I decide, okay, well, let's try to turn this into sine and cosine and see where that takes me. So tangent, remember, is the same thing as sine squared over cosine squared. Tangent squared x is the same thing as sine squared x over cosine squared x. And then secant squared x is the same thing as 1 over cosine squared x. Well, again, once you kind of get the ball rolling, you start to see things that you can do. Oh, now I have a fraction divided by a fraction. If I have a fraction divided by a fraction, that's the same thing as taking this top fraction and multiplying it by the reciprocal of the divisor. So this ends up becoming sine squared x over cosine squared x times, and then the reciprocal of the divisor is now cosine squared x over 1. And what happens is I get cosine squared and cosine squared, they're going to cancel out. And so the end result here is sine squared x. So this expression simplifies to be sine squared x. Now, is that the only way to do this problem? No, that's the first way I saw it. I'm actually going to do it another way, just so you can see. I mean, there's not always one right way to do this. Sometimes you see a certain way and then someone else shows you a different way. Sometimes it's more simple and elegant. Sometimes it takes longer. I'm going to show you a different approach to this without using the substitution that I did there. So I'm going to go back to the beginning here. So starting with this same trig expression, well, another thing I know I can do, I only have one term in the denominator. Just, before I do what I'm about to do, I want to make sure you're clear on something. If I had 1 plus 4 over 4, That's the same thing as 1/4 plus 4/4. Right? If I have this fraction here, I can split the fraction into two different fractions, keeping the same common denominator there. Well, I know that that's true, and I can apply the same thinking here. I only have one term down here, and so I can simply split this up into two separate fractions. I could write this as secant squared x over secant squared x minus 1 over secant squared x. Again, I still have denominators of secant squared x. I simply split the fractions up, much like I did here. Well, secant squared x over secant squared x is just 1 minus 1 over secant squared. Remember, secant squared is the reciprocal of cosine. So this is really cosine squared x. And like we saw in the previous video, we wind up with this kind of expression a lot, either 1 minus cosine squared or 1 minus sine squared, based on that first, the more common Pythagorean identity. And so 1 minus cosine squared, well again, that's the same thing as sine squared x. So I did this problem two different ways. The other way, I guess, took a couple more steps. Either way was fine. I still got the result that I was supposed to get. So again, there's no one way to do it. You know, if you're doing something and it's taking you 12 steps, well, maybe try a different approach. Okay, typically these problems aren't supposed to take that many steps. And again, if you're working with someone on this, maybe you try it one way and you get a certain method and you do it, and they try another way. Maybe it's a little bit longer, maybe it's a little bit shorter. But ultimately, one of the goals in math when you are doing stuff is, well, you want to be able to do things a lot of different ways so you can, tackle various kinds of problems as they come to you. But a lot of times, especially in a case like this, we're usually seeking the more elegant, the more simple way to do stuff. So if I had to choose between the two methods, I'd probably say this method was a little bit more efficient, a little bit faster than the other way I did it. But either way is fine. Okay, let's do number 17. So number 17, I had 1 plus cosecant of x on top. In the denominator, I had cosine x plus cotangent of x. Cosine of x plus cotangent of x. So I'm going to write that down. I'm looking at this, and again, my first inclination is to look for any of the identities we already have in our notes. Nothing really stands out. I mean, that's just a bunch of terms. So again, a lot of times my fallback is, well, maybe something will come as a result of me turning into things of sine, or things in terms of a sine and cosine. So 1 is just 1, plus, well, what is cosecant? Cosecant is 1 over sine x. In the denominator, that's already in terms of cosine, so that's cosine x, plus, and then cotangent of x. Well, what is cotangent of x? Cotangent of x is cosine of x over sine of x. So again, I started at the beginning of this problem, and I couldn't really think of a way to do this, as far as identities go. So again, one of the things we try a lot is just, well, let's turn things into terms of sine and cosine, and maybe that will get us somewhere. So that's what I've done so far. And then, well, now I have this on top, I have this on the bottom, but now suddenly I have these fractions. And so things that I typically will try in a case like this is, okay, well, maybe if I make common denominators, then, I'll get the ball rolling and I'll get somewhere. So if I look at the top of this fraction, I have 1 plus 1 over sine x. Well, so the common denominator here would clearly be sine x. So I can rewrite 1. 1 is the same thing as sine x over sine x, plus I still have 1 over sine x. And I can do the same thing in the denominator. In the denominator, this is cosine x, but that's cosine x over 1. So again, if I'm looking to make common denominators here, the common denominator is sine x. So I'd multiply the top and the bottom of this fraction by sine x over sine x. So if I do that in the denominator, I would get sine x times cosine of x over sine of x. Plus, here I have cosine x over sine x. Okay, so again, to recap what we've done so far, this is my expression. There weren't any identities that jumped out at me. And so I thought, well, let me turn things into terms of sine and cosine. So that's all I did here was turn things into terms of sine and cosine. From there, since I had these, well, this is a fraction, this is a whole number fraction, and this was an expression I can put over 1. But I thought, well, maybe if I make common denominators here. So this is where I'm at now. So on the top right here, I can combine that into one fraction, so this would all be over sine x. So on top I would get sine x plus 1. So I have sine x plus 1 all over, so that's that big fraction bar there. And again here, I can also write that as one fraction that's all over sine x. I get sine x cosine x plus cosine x. So I get sine x cosine x plus cosine x. Well, now I have a fraction divided by a fraction. So what are we going to do when we have a fraction divided by a fraction? I'm going to take this fraction and multiply it by the reciprocal of the divisor. So this is the same thing as sine of x plus 1 divided by sine of x times the reciprocal of this, which is sine of x over sine of x cosine of x plus cosine of x. Well, sine of x can cancel out with sine of x. Now, nothing else cancels straight away here. However, if you look at this fraction here, in the denominator, I have this term and I have this term. If I think about factoring, if I think about taking out the greatest common factor of sine x cosine x plus cosine x, well, they have a factor of cosine x in common. So I can factor that out. So I still have the sine x plus 1 over 1, because remember this canceled out, times, on top here I have a 1. In the denominator, if I factor out the cosine x, if I factor out cosine x from this term, it still leaves me with sine x. Plus, if I factor out cosine x from this, it just leaves me with 1. And then the sine x plus 1 and the sine x plus 1 cancels. And so now all I'm left with is 1 over cosine. 1 over cosine is better known as secant x. So this expression turns into secant x. Okay, let's do another one again. I'm doing some of the ones from the assignment I put on Aries simply because, I did some in the notes on the last lesson, but, I'm limited to kind of the examples that I have. I pulled out another textbook to get some more examples, but I kind of feel like, if I don't show you some specific hard ones, you may feel like, oh, you only did the easy ones in the notes and you left all the hard ones for the assignment. No, I'm going to try to mix it up, try to make sure there's some easier ones so you get the idea, but also throw in some hard ones. So let's look at number 19 now. So 19, I have 1 plus sine u over cosine u. So 1 plus sine of u over cosine of u. And then plus cosine of u over 1 plus sine u. So essentially I have this plus its reciprocal. So I look at that. When you guys hear a pause, it's probably because I'm drinking. So I've got my water like I typically do. So anyhow. When I look at this, again, the first thing I look for is, do I have any identities that jump out at me? I don't see anything. So then my next thought is, well, okay, turn things into terms of sine and cosine. But that's already done. Everything up there is already in terms of sine and cosine. So then my next thought is, well, okay, well, what can I do? Well, I do have two fractions. So if I do have two fractions, I could always just find common denominators. In this fraction, I have a denominator of cosine of u. In this fraction, I have a denominator of 1 plus sine of u. So the common denominator would simply be this factor times this factor. So that means on this side, on this fraction, I need to multiply by 1 plus sine u on the top and the bottom. So that would give me 1 plus sine of u over 1 plus sine of u times this fraction that's sitting here, which is 1 plus sine of u over cosine of u. Okay, plus, and then, well, this denominator already has 1 plus sine of u. I need the other factor, which is cosine of u. So here I need to have a cosine u over a cosine u. So I'm going to take this fraction, and I'm going to multiply it by cosine u over cosine u. So again, I'm just taking the original two fractions, I'm multiplying them by forms of 1, but now that I've done that, now I have the same denominators, right? They're made up of the same factors. A factor of 1 plus sine u and cosine u, a factor of 1 plus sine u and cosine of u. Now on top, well, I have 1 plus sine u times 1 plus sine u. Well, that's like a plus b times a plus b. We should remember that a plus b squared is a squared plus 2ab plus b squared. I mean, you could just multiply it out, but if I have a plus b times a plus b, which is really a plus b squared, it's a squared, so a in this case is 1, so that's 1 squared, which is 1, plus 2ab, in other words, 2 of this times this. So 2 of 1 times sine is 2 sine of u, and then b squared. So sine of u times sine of u is sine squared. Okay, now that's if you remember a plus b squared, what that results in, again, a squared plus 2ab plus b squared. I mean, you could always multiply this out. 1 times 1 is 1, 1 times sine u is sine u times 1 is a second sine u, so that's why we have 2 sine u's, and then sine u times sine u is sine squared u. In the denominator, I know I mentioned this in the last video as well, but in the denominator, I typically don't want to multiply that out. I want to leave it in factored form. Because if I leave it in factored form and something happens to be able to cancel out, in another step, it'll be easier to see if I left the denominator factored. So for now, I'm going to leave the denominator factored as 1 plus sine of u times the cosine of u. Okay, over here I have cosine u times cosine u on top. That's cosine squared u. In the denominator, again, I won't multiply that out. I'll just simply leave it in factored form. 1 plus sine of u times the cosine of u. So, well, now that I've made common denominators, I can combine these two fractions into one fraction all over the common denominator, which is 1 plus sine of u times the cosine of u. And let's see what we get on top. We have 1 plus 2 sine u plus sine squared u plus cosine squared u. So I have 1 plus 2 sine u plus sine squared u plus cosine squared u. When I look at that result, I mean, there's a lot of terms on top, but when I look at these two right here, well, what's sine squared u plus cosine squared u? That's the basic Pythagorean identity. That's just equal to 1. So this is just equal to 1. So now I have 1 plus this 1. So now I just have a 2 on top. I have 2 plus, I still have 2 sine u. In the denominator, I still have 1 plus sine of u times cosine of u. Can I cancel anything out right now? No. But, I mean, 1 plus sine u and 2 plus 2 sine u are almost the same. What do I have on top as a GCF? The greatest common factor of these two terms is at 2. So if I factor out the 2, it leaves me with 1 plus sine of u. In the denominator, I have 1 plus sine of u times cosine of u. Now I can cancel out these factors. 1 plus sine u divided by 1 plus sine u, that's equal to 1. And now I'm left with 2 over cosine of u. Well, having cosine in the denominator is the same thing as turning that into 2 times the secant of u. So this expression becomes simply 2 secant of u. And again, I mentioned this in the last video. Why are we practicing this so much? Well, I mean, it's useful just in terms of algebraic manipulation and understanding various identities, and it's just good practice for, if you want to get good at trigonometry. But the other aspect of it is, again, if I encounter something like this in calculus and I have to do something with it, typically what we end up doing in calculus are things, called derivatives or antiderivatives. Taking the derivative or the antiderivative of that expression takes a lot of work. But if I know that this expression is equal to this expression, well, taking the derivative of this is really pretty easy. And taking the antiderivative of this is a little bit harder, but it's still not that bad. A lot easier to deal with this expression than it is to deal with this expression. Okay, so I'm going to write that down if you haven't already got that. So that was number 19. We're going to do one more from that. We're going to do number 21, and then I'm going to move on to the next section. Again, if you are doing the assignment from Aries that I put for extra credit, I know I'm showing you how to do several of the problems from that assignment, but if you're just going to simply copy from the notes into a homework page and turn it in for credit, yeah, you'll get the extra credit points, but I mean, great, like, are you really going to know what you're doing? If you encountered a problem like that, next year, are you going to know what to do? So keep that in mind. I mean, don't just artificially inflate your grade just for the sake of having a high grade, when really, it's better if you actually know this material. Okay, so number 21. Number 21 says 2 plus tangent squared x over secant squared x minus 1. So 2 plus tangent squared x over secant squared x minus 1. So, well, there aren't any identities that are necessarily jumping out at me. I mean, I do see the tangent square, but then there's this 2 here. We don't really have an identity that has the 2 like that yet. But I do have this fraction, and then I do just have a minus 1 sitting here. So a lot of times with fractions, again, if I can't think of anything else to do, I may just say, well, why don't I make common denominators and at least combine them in one fraction? So if I do that, I would get 2 plus tangent squared x over secant squared x minus, well, what is 1 if I'm making common denominators? Well, my common denominator clearly is secant squared, so I can rewrite 1 as secant squared x over secant squared x. So this becomes secant squared x over secant squared x. Well, now that I have it all as one fraction, or common denominators, I can write it as one fraction. So I'm going to write the whole thing over secant squared x. So now I have 2 plus tangent squared x minus secant squared x. So 2 plus tangent squared x minus secant squared x. Again, I'm kind of looking for stuff. I do know I have an identity that involves tangent squared and secant squared. If you recall, we have this identity, 1 plus tangent squared x equals secant squared x. It's one of the 3 Pythagorean identities. Well, what do I have here? I have tangent squared minus secant squared. Can I replicate that over here? Well, yeah. If I want to get tangent squared minus secant squared, I can simply subtract the secant squared to this side. But what I would want on this side is simply tangent squared minus secant squared. So if I'm going to subtract the secant squared to this side, I probably want to get rid of this 1, which means I need to subtract it to the other side. So an equivalent form of that Pythagorean identity would simply be tangent squared x minus secant squared x equals negative 1. So again, all I've done is I moved this term to this side and this term to the other side. Well, look at that. Now I have tangent squared minus secant squared, which is exactly what I have sitting right here. So tangent squared minus secant squared can be substituted for a -1. So very quickly this turned into 2 minus 1 on top. In the denominator, I have secant squared x. Well, 2 minus 1 is 1 over secant squared x, but 1 over secant squared is the same thing as cosine squared x. So again, I did several problems from that first Aries assignment. These are the ones I thought maybe would give people the most trouble. Again, I wanted to show you just as much as I can different thought processes I go through when I'm simplifying these. Okay, and there's certain things that I think about a lot. Identities, maybe I turn things into sine and cosine, maybe I make common denominators. Okay, there's a lot of commonalities to these. Every single problem's a little different, but in my mind I kind of go through this checklist. What could I try? What could I try? And again, with anything, the more you practice these, the better you'll get. So if you're sitting there at home and you're like, oh my gosh, I'm terrible at this, like I haven't gotten one right yet. Well, that's okay. We barely started this. You're on what, day 2 of this at most. So don't worry about it. You'll get better as time goes on. Okay, before we do anything new, I want to do one more problem from that assignment on Aries. This time it's the identities. So I'm going to do number 29 because I thought, well, 29 might cause a little bit of issue for you guys. So on 29, I have the tangent of y over the cosecant of y, and that's supposed to be equal to the secant of y minus the cosine of y. So this is where we're at. Now, again, I mentioned yesterday when you're doing these identities, you only want to work with one side. And so I want to either choose the left-hand side or the right-hand side. Typically, you're trying to choose the side that looks more complicated. But, I mean, I could probably do this fairly simply using whichever side, either the left-hand side or the right-hand side. So for me, I'm probably going to use the left-hand side simply because, well, on the left-hand side I have one term, just this fraction. And when I have fractions, I typically have more in my wheelhouse as far as what might I try to do. And I could think about the same thing here as well, but here I'd have to take two terms and combine them into one. I could go about it that way, but again, it's really up to you. I'm going to do it with the left-hand side. I think the left-hand side might be easier to do. So, on the left-hand side, I just have this fraction. What am I going to do with this fraction? Again, my first thought is, well, do I have any identities? Well, not anything, nothing's jumping out. There's no Pythagorean identities or anything like that. So then again, our fallback is a lot of times rewriting these expressions in terms of sine and cosine. Okay, so what is tangent? Tangent is sine of y over the cosine of y. And then what is cosecant? Cosecant is the reciprocal of sine, so that's 1 over sine y. Again, make sure you're bringing down that equal sign. You don't have to rewrite this side, but you want this trail of equal signs, so eventually when you make this left-hand side look like the right-hand side, you have this trail of equal signs showing that yes, both sides are equal. Okay? Well, so now I have this fraction divided by this fraction. Now we seem like this comes up quite a bit for us. When I have this fraction divided by this fraction, it's the same thing as this fraction times the reciprocal of the divisor. So this is the same thing as sine of y over the cosine of y times, well, the reciprocal here is going to be sine of y over 1. Again, there's my equal sign again. So, well, this is where we're at. If I simplify this, in other words, if I carry out the multiplication, what do I get on top? Sine of y times sine of y is sine squared of y. In the denominator, cosine y times 1 is simply cosine of y. Well, I have everything in terms of sine and cosine. I'm trying to make it look like this. And so this is, we've done the things we've talked about. I turn this into terms of sine and cosine. I have a fraction divided by a fraction. I multiplied by the reciprocal. But this is where I'm at now. And this is not what I'm trying to get to. Sometimes you'll get to a point in one of these identities where you're sort of stuck. You don't really know what to do. And if you peek at the other side, so I'm peeking at the right-hand side now. And one thing I do know about the right-hand side is that there are two terms here. And right now I just have this term. Just one term here. So somehow I'm going to have to be able to turn this one term into two terms. So if I look at this a little while longer, sine squared. What could I turn into sine squared? What can I replace sine squared with? Again, this keeps going back to basic identities. Sine squared y, well, that's the same thing as 1 minus cosine squared y. Again, we've seen that Pythagorean identity get manipulated a bunch. So if I have a sine squared y, I can rewrite sine squared as two terms. And again, I'm trying to rewrite and make it look like the right-hand side where I have two terms. So I can replace sine squared with 1 minus cosine squared y over cosine y. That gives me two terms on top. I'm getting closer to having a result of two terms. Now from here, well, like I showed you on a previous problem, I just have this denominator of cosine y. I have two terms on top. If I want to, and I do want to, I can split that fraction up into two fractions. I can rewrite this as 1 over cosine y. So I have 1 over cosine of y minus, and then I have cosine squared y over cosine y. Well, now I have two terms. I have this fraction, I have this fraction. Now I have two terms. And let's see if I can simplify this. What do we call 1 over cosine? Well, 1 over cosine, that means the reciprocal of cosine. The reciprocal of cosine is in fact secant. So this now becomes secant of y minus, and then, well, I have cosine squared divided by cosine. If I had cosine squared divided by cosine, one of these cosine factors on top are going to cancel out with that one, but I still am left with one more factor of cosine. And suddenly I have secant y minus cosine of y, follow my equal signs up, equals secant of y minus cosine of y. Again, like I mentioned yesterday in the previous video, do not stop working on one side until you have exactly written what's on the other side. Don't stop here and say, well, yeah, that's the same thing as that. You need to write it so this and this have the exact same thing there. Okay, don't stop before then. Okay, so that's all I'm going to show you from that assignment I posted on Aries. And then the remainder of this video, I'm just going to do some more identities that I've chosen out of the book. I'm going to do some of the even ones, and then I'll post an assignment on Aries that'll be some of the odd ones. Okay, so the next problem I'm going to do, it's a pretty simple one. It's number 32 out of the book. It has cosine of negative x minus sine of negative x plus sine of x. So, first things first, I need to decide, well, which side of the equation will I choose to work with? I'm typically looking for the more complicated side. I would say the left-hand side is slightly more complicated. And really what I'm looking at is the fact that the arguments here have negative x's in them. So if we think about the identities we have in our notes so far, we have the basic reciprocal identities, we have the Pythagorean identities, we have the even and odd function identities, and we have the cofunction identities. Well, let's back up a little bit. In our notes, we have the even and odd function identities. We know certain things about both sine and cosine. Cosine of negative x, well, what kind of function is cosine? Cosine is an even function. We discussed that in class before. And so what does it mean to be an even function? It means that f of negative x equals f of x. So I'm going to work on the left-hand side because this negative argument here gives me something I can try to work with. I know that cosine is an even function, so that means that cosine of negative x is the same thing as cosine of x. And I have that minus sign. And then it brings me to sine of negative x. Well, what do we know about sine of negative x? We're going back again to these identities we have in our notes. Sine is an odd function. Well, the definition of an odd function is that f of negative x is equal to negative f of x. So I already have this minus sign because it was part of the equation. But what I can replace sine of negative x with is negative sine of x. Again, don't forget your equal sign. Well, just by applying the even and odd properties here, now I'm just subtracting that negative, so I can rewrite this as cosine of x plus sine x, and 2 steps we're done. So when I see stuff like this, when I see that the argument is suddenly negative instead of just being x or theta or whatever the argument was, immediately alarm bells go off in my head and I start thinking, well, that's got to be something to do with even and odd functions. Okay, we have all the even and odd functions in our notes, so apply those properties. So when you see anything in the assignments that has the negative sign in the argument, in all likelihood it means, okay, you need to apply even and odd identities there. Okay, so that was number 32. Let's look at another problem. I'm going to look at number 34. So number 34, I have cosecant of x times cosecant of x plus sine of negative x. And that whole thing is supposed to be equal to cotangent squared x. So again, the first thing I'm going to do is think about, well, which side do I want to work with? Which side is more complicated? I think the left-hand side is more complicated. I mean, this factor on the outside of the parentheses is something I could distribute if I chose to do. I also have a negative argument here, which again alerts me to the fact that I should probably use even and odd identities there. The other side, cotangent squared x, not as much to work with. I mean, what am I really going to do with cotangent squared x? So I'm going to choose to use the left-hand side. So probably the first thing I'll do is I'll simply remove the sine of negative x and replace it using the fact that sine is an odd function. So all I'm going to do for now is write this as cosecant of x times cosecant of x. But then remember, sine of negative x, since sine is an odd function, is the same thing as negative sine of x. So this is where I'm at. So now I have cosecant times cosecant. Well, that's just cosecant squared. So cosecant squared x minus, well, now I have cosecant times sine. So all I'm doing is distributing this factor. Okay, cosecant times cosecant, that got me cosecant squared. And then cosecant x times sine x. Well, what do we know about cosecant and sine? Well, they're reciprocals of each other. So again, if I take 2 factors that are reciprocals of each other, the result should be 1. And so now I simply have this. Cosecant squared x minus 1, what am I trying to get? I'm trying to get cotangent squared. So this is where, again, it's really, really, really important. As we add to our bank of identities, we want to make sure every time we get a new set of identities, we are learning the new ones, but also just keep rehashing, keep going over the old ones. We have 3 Pythagorean identities. One of our Pythagorean identities is this one. Cotangent squared x plus 1 is cosecant squared x. What do I have here? I have cosecant squared x minus 1. So if I take a look at this Pythagorean identity that we have in our notes, if I manipulate this to make it cosecant squared x minus 1, all I would need to do is subtract the 1 to the other side. And if I do that, the result is I get cotangent squared x equals, cosecant squared x minus 1. Well, this is exactly what I have. And so what can I substitute for cosecant squared x minus 1? Oh, well, that's simply cotangent squared x. So I can make that substitution, and suddenly I'm at the end of that problem. Okay? I made the left-hand side look like the right-hand side. Okay? Let's try another one. I'm going to look at number 36. 36, I have sine x plus cosine x, that whole quantity squared, is equal to 1 plus 2 sine x cosine x. I'm going to write that down. So, again, my thoughts are, well, which side do I want to work with? On the left-hand side, I have this quantity squared, so in the very least, I have something that I could multiply out. I could square that side. On the right-hand side, I have 1 plus 2 sine x cosine x. I don't see any identities that you're aware of yet. I don't see anything that can factor. It's already in terms of sine and cosine. So I probably don't really want to use the right-hand side because, again, it would be more difficult, probably take more steps. As a practice for you guys, if you guys are flying through these, if you're getting really good at verifying these identities, some of you have more experience than others doing these, one thing you can practice is maybe doing it on the left-hand side, and then once you've seen it on the left-hand side, go back to the beginning and then try to do it on the other side, see if you can do it. A lot of times, once you've done it on one side, then when you go back and you start over and you use the other side, it's essentially your reverse engineering. You know how the left-hand side went, and so now it's just a matter of undoing those things on the right-hand side. But anyways, I think I'll start with the left-hand side here. I have sine x plus cosine x squared. Again, that's like having a plus b squared. Well, a plus b squared, recall, this is from earlier in the year, a plus b squared is equal to a squared plus 2ab plus b squared. Despite what that poster by the pencil sharpener says, this is how this multiplies out. The only time that a plus b squared is a squared plus b squared would be, like I mentioned before, in a commutative ring mod 2. But you're not an abstract algebra, so you don't need to worry about that. Anyways, since I know how that should square out, if I know how this binomial squared should multiply out, I know this is going to become sine squared x plus 2 sine x cosine x plus cosine squared x. In other words, it's a squared plus 2ab plus b squared. Again, don't forget your equal sign. So we've squared that binomial quantity. And so, do you see it? We're one step away. I'm going to write one more line and then we're done. Because I took this, I squared it, I have this. Once I carry out a step, I look, and again, my thought processes are, well, what can I do now? Do I see identities and so on? Well, I do see an identity. I have a term of sine squared x, plus I have another term of cosine squared x. Well, that should be kind of ingrained in our minds at this point. I have sine squared x plus cosine squared x. Well, what is that equal to? Sine squared x plus cosine squared x is 1. Plus, I still have the factor, or the term of 2 sine x cosine x equals, well, that's what I was supposed to equal. I'm done. This took all of, 2 steps? Okay, so some of these are very quick, especially if you see exactly what to do. But again, Don't sit there at home and say, oh my gosh, I've been doing this for 15 whole hours in my life and I'm not as good as Mr. Palmer. Well, obviously, I've been doing this for a long time, like since the early 30s, like right after the Great Depression. I just sat in my room and I just did trig identities over and over and over. It helped me get over the market crash. Okay, let's look at number 38. I have cosine x over secant x plus sine x over cosecant x, and that equals 1. Go ahead and write that down. So again, my first thought is, well, which side do I want to work with? On the left-hand side, I have a couple of fractions. On the right-hand side, I have 1. So which side is more complicated? Well, clearly, it's the left-hand side. Now, could someone, if they were really good, do the right-hand side? Yeah. But again, a lot of times doing the right-hand side or the side that's less complicated, you would usually approach that maybe after you've already done the more obvious side to work with and then kind of reverse engineer it. Okay? But I think you're clever enough to do the right-hand side if you so choose. But I'm not going to do that here. I'm going to look at the left-hand side. I don't have any identities that jump out at me, but again, I see this relationship. We did a problem in the previous video, very similar to this. And when I look at this, well, I have a relationship between cosine and secant. I have a relationship between sine and cosecant. They're reciprocals of each other. And so if I simply turn everything in terms of sine and cosine, my steps start to become obvious. So I have cosine x still, but what is secant? Secant's the reciprocal of cosine. Secant x becomes 1 over cosine x. Plus, here I have sine x over cosecant x. So that's going to be sine x over, well, cosecant x is the reciprocal of sine, so that's 1 over sine. Again, put your equal sign. So now we're here, but again, always, it's like I do a step and all of a sudden things start falling into place. You know, you get that one thing started and your steps start to become obvious. Well, look, I'm dividing by a fraction. I'm dividing by a fraction. What do we do when we divide by a fraction? We multiply by the reciprocal. So now I'm going to take cosine of x times the reciprocal of this is the cosine of x over 1 plus, here I have sine of x times the reciprocal of 1 over sine x, which is sine x over 1. So cosine of x times cosine of x over 1 is simply cosine squared x, plus sine x times sine x over 1 is really sine squared x. And again, for about the 48th time in the last 2 videos, what's cosine squared x plus sine squared x? It's just 1. If you know no other identities, you got to know this one. Okay? It comes up a lot. Cosine squared x plus sine squared x is equal to 1. What was I trying to equal? I was trying to equal 1. Again, problem's done. Okay, let's do one more problem and then we'll call it a video. So I'm going to do number 40. This is sine x plus cosine x to the 4th power. And that equals 1 plus 2 sine x cosine x squared. So, I'd say both sides of this equation look fairly complicated. Now I'm going to think back to a previous problem we've already done in this video. We had a problem earlier in this video where it was sine x plus cosine x squared, and then on the other side here we had 1 plus 2 sine x cosine x. So it's like that previous identity, the only thing is they just squared both sides. So I'm going to still choose to work with the left-hand side, and this is what I know on the left-hand side. I know that sine x plus cosine x to the fourth, well, that's the same thing as sine x plus cosine x squared times sine x plus cosine x squared, right? This times this is really just that. Well, again, this is just from a previous thing we did in this video. If I square this binomial, again, this is like a plus b squared. So if I square sine x plus cosine x, I know that this becomes sine squared x plus, so this is a squared plus 2ab. That's going to be 2 sine x cosine x. And then plus b squared. So plus cosine squared x. So sine x plus cosine x squared, that's a squared plus 2ab plus b squared. In other words, it's sine squared plus 2 sine x cosine x plus cosine squared x. Well, that's just from this. Well, we're still multiplying times this, so I just get a second one of those. I have sine squared x plus 2 sine x cosine x, plus another cosine squared. So plus cosine squared x. Again, squeezing my equal sign there. But similar to what happened on the previous problem where we did this, when I look inside here, I see that I have sine squared plus cosine squared. Well, again, I know that sine squared plus cosine squared is still just equal to 1. So what I get inside there is I get 1 plus 2 sine x cosine x. Well, if that happened here, it's going to happen here as well, because again, I have sine squared x and cosine squared x. Again, that's 1. So that becomes 1 plus 2 sine x cosine x. Well, if I have something times itself, that's the same thing as having that quantity squared. So now on the left-hand side, it becomes 1 plus 2 sine x cosine x squared. That was what I was supposed to get, and we're done. So try these, work with them. You'll get better at them, I promise. We're going to spend several days on these, because the next step after this, after we get really good at these, and again, we'll spend some time on these, but after we get really good at these, we're going to start solving trig equations, and trig equations have, some aspects of it relate to being able to do stuff like this, verify identities, simplify trig expressions. Some of it relates back to the unit circle. Some of it relates to our knowledge of the trig graphs. So this is just another kind of step along the way, working ourselves towards being able to solve trig equations. Now, trig equations, again, they come up in calculus next year. Sometimes you get an equation, it's a trig equation, and you have to solve it for certain values of x or theta or whatever the variable is. Okay? So, anyways, hope you're able to follow along. Hopefully this video was better than the last one. At least my editing won't be as poor, I hope. So, anyways, until next time, have a good night.